my name is Joey Zegar, and I'm here to teach you analytical chemistry. Now, I know it can be a little intimidating, and sometimes you just want to throw yourself off a cliff, but I assure you, after this helpful video, even you will be ready to conquer any problem Dr. Samad can throw at you. The first concept we're going to go over is concentration. There are two types of concentration you need to know for this problem, and they're both fairly simple to understand. They include molarity and weight percent. Now, I'll first go over molarity. I'm sure you may have used it before, and it's fairly simple. Molarity is defined as the moles of solvent over liters of solution. For example, let's look at a beaker which contains 1 liter of water. If I add sodium chloride in enough mass so that I've added 2 moles of sodium chloride, the solid will dissolve and form sodium and chloride ions so that there is 2 moles of sodium ion and 2 moles of chloride ion. Now, since we have 2 moles of this in 1 liter of water, we can now determine that this is a 2 molar solution for both sodium and chloride ion. Another example of concentration is weight percent. This is probably a bit less familiar to most of you, but it's still very important and easy to understand. Weight percent is defined as the mass of solvent over the total mass of solution times 100. For example, something very commonly used in chemistry is 95% ethanol. To make this, you would take 95 grams of ethanol, add 5 grams of water, and that's about it. This makes sense because if you think about it, you have 95 grams of ethanol, the solvent, over 100 grams of total solution. Therefore, it's 95 over 100 times 100 to get 95% ethanol. Stoichiometry is another important concept for this problem. Stoichiometry is the area of chemistry concerned with products and reactants in a chemical equation. In order to apply stoichiometry, a balanced equation is required. For example, let's consider the combustion of propane. For this, you'd have the equation 1 mole of propane plus 13 halves moles of oxygen yields 5 moles of water and 4 moles of carbon dioxide. In order to compare amounts of products and reactants, the coefficients of each product and reactant must be taken into account. As is shown in the equation, combusting 1 mole of propane used 5 moles of water and 4 moles of carbon dioxide. While this is a fairly simple concept to understand, it is crucial because failing to pay attention to coefficients can drastically change the results of a problem. The final concept needed for this problem is excess. Normally, we set up reactions so that all the products are used and nothing's left over. However, sometimes it is necessary to have some amount of product remain. This is where excess is important. For example, let's assume a problem asks for a reaction completed with 75% excess sodium chloride at the end. Let's say we go through the work and find that initially we need 10 grams for this reaction to run to completion. However, if we use 10 grams, there's nothing left over, and we won't get the problem right. So we need to account for the fact that we need 75% more than we think. To do this, we're taking the amount of sodium chloride we do need, the 10 grams, and add 75% of 10 grams, or 7.5, in order to find the total amount we want to add for this reaction to be successful and still have some left over. The specific problem I'll focus on today is problem 6 from chapter 1, which reads, how many grams of 0.491 weight percent hydrogen fluoride are required to provide a 50% excess to react with 25 milliliters of 0.0236 molar thorium-4 ion. Now, the first step of this problem is to determine how much thorium we actually have in the solution. A simple conversion is needed to do this. Now, as I explained before, molarity is moles per liter. So to find moles, we just have to multiply it by the liters of solution we have, which in this case is 0.025, or 25 milliliters. Once you do this, you'll find that we have 5.9 times 10 to the negative 4 moles of thorium ion. The second step is to figure out how much fluoride we need to react with this. Now, as you can see from the equation, the stoichiometry shows that it is not a 1-to-1 ratio, but rather a 4-to-1 ratio, which is a bit trickier. So, in order to find the total moles we need, we have to multiply the thorium ion amount by 4. Once you do this, you'll find that we need exactly 0.00236 moles of fluoride. It was at this point that I decided to account for the excess requested. Now you can do this later if you want, but I chose to do it now. In order to do this, I multiplied the moles I need by 1.5, or 150%, to find the total amount I want to add. From doing this, I found that I need 0.00354 moles of fluoride. Now, the problem is, we're getting our fluoride from hydrogen fluoride, and the weight percent is based on that, and not the amount of fluoride. So we have to somehow take our moles of fluoride and get grams of hydrogen fluoride. This isn't too complicated though. First, we know that there's a 1-to-1 ratio between fluoride ion and hydrogen fluoride. So if we need 0.00354 moles of fluoride, we would also conveniently need the same amount of hydrogen fluoride. The next step is to convert this amount to grams. Now, I conveniently know that the molar mass of hydrogen fluoride is 20.006 grams per mole. Therefore, by multiplying the amount of moles we need by this value, we find that we need 0.0708 grams of hydrogen fluoride. The last thing we need to do is take this amount and somehow change it into amount of solution. Now, since we know that in 100 grams of solution we have 0.491 grams of hydrogen fluoride, we can multiply the grams we need by this ratio of 100 over 0.491 and find the grams of solution we need. By doing this, you will find that we need exactly 14.4 grams of the hydrogen fluoride solution. Therefore, after going through all of this work, we have determined that to successfully cause the reaction as described in the problem, we need to add 14.4 grams of the 0.491 weight percent hydrogen fluoride solution. Besides the examples given in the book, let's look at one more problem that uses the concepts we've gone over. Now, let's suppose that there is a 12 milliliter solution with 0.128 molar calcium ion, and that we want to remove all of this calcium ion with a 23.3 weight percent hydroxide solution, and that we want 100% excess of this hydroxide at the end. Now, stop the video for a few moments and try and work through this problem. Then, I'll go over it and we'll see if you got it right. Alright, now the answer you should have gotten is 0.451 grams of hydroxide solution. In order to do this, we once again find the moles of calcium ion in the solution and use stoichiometry to convert this value to moles of hydroxide solution. Note that it's a 2-to-1 ratio. Now since the problem asks for 100% excess, we simply need to double the moles of hydroxide we need. Next, like the first example, we need to convert the moles into grams and then use the conversion of weight percent to find the total grams of hydroxide solution we need for this problem to be successful. If you do it right, you should find that 0.451 grams is required. Well, that about wraps up my explanation of my analytical chemistry problem. I hope it was helpful and that you learned something along the way. In closing, I wish you the best of luck with the rest of our class. And as always, stay classy, Butler University.